I came across this video from NASA claiming that they were going to fly a drone on Mars. No, because Mars has about 1/100th the atmosphere of Earth. So how are they going to fly in an atmosphere that thin? Now, I've called out NASA when they've come out with bullshit before, most notably when they claim that they found arsenic-based life.
Well, a mysterious NASA press release sparking major attention. They're holding a press conference this time tomorrow afternoon to announce, quote, an astrobiological finding that will impact the search for evidence of extraterrestrial life.
What we think is happening, what all the evidence we've collected suggests, is that instead of these, we'll see these orange, light orange balls disappear. And represented by green balls, we see that arsenic would be substituting for phosphorus in the backbone of DNA. And you can see how critical this component of the DNA might be.
Turned out, they just kind of analysed some dirty samples. Yeah, who would have seen it coming? Now, it's got to be said that I've taken a look at some of NASA's early landing on Mars type sequences and thought, not a chance in hell. Now, sure, I never made a video on it or anything, but that's what I was thinking. There was just so many things that had to happen correctly in sequence, it was just crazy. So take, for instance, Spirit and Opportunity. After 6 months in space, the first thing that you have to do is hit this incredibly narrow atmospheric window and lose some speed. Then you deploy a parachute and lose the heat shield, descend on a rope, inflate some airbags, fire the retros at exactly the right altitude in a second specific window. Then bounce around for a bit, deflate the airbags, maybe right the tetrahedron, and then have the rover unpack itself sufficiently unbumped by all of the knocks that it's had that it actually rolls off the platform in a functioning form. And I took a look at that and thought, no way, there's just so many things to go wrong. Then, some years later, came the Curiosity rover, which was a big boy and used something called Sky Crane to lower itself to the surface via a sort of rocket-suspended platform. Now, these achievements are very impressive because of the technical challenges of packing everything that you need onto a rocket and leaving it there for the best part of a year, and then timed to the second everything has to go right on Mars, because none of this can be joysticked, if you like. It's all got to be automated, because at best it takes about 4 minutes to get a radio signal to Mars and 4 minutes for the return, so that's about 8 minutes. Or at its worst, when Mars is on the other side of the sun, it takes about 40 minutes to get a reply from Mars. So all of this has to be automated. Which brings us to flying an automated drone on Mars. Yeah, I'm skeptical about this one. The principal problem is that Mars doesn't have much atmosphere, so how are you going to produce the lift to get this off the ground? Hell, to get an atmosphere this thin on Earth, you have to go up about 3 times the height of Everest. Now, you are actually helped out a bit by the fact that Mars is significantly smaller than Earth and only has about 1/3 of the gravity, so you only have to produce about 1/3 of the thrust to get something airborne. However, getting 1/3 of the thrust from 1/100th of the atmosphere is challenging. Even more challenging is this isn't like landing where it's got to go right once. This has to go right again and again and again because it's going to fly multiple times, with obvious challenges like the wear and tear to the rotors. And as every drone pilot will tell you, once these things crash and they fall over, they don't take off again. Right? You actually have to stand them up before they will fly again. That's easy enough to do when you're on Earth, but it's got to be one of the most infuriating things ever to have a drone fall over on Mars, because it's going to be an awful long time before anyone can stand it up to fly again. Right, so to get the thrust, helicopters typically angle their blades, and then they swing them through the air, batting the air molecules downwards, and this produces thrust upwards. And of course, it sort of slows the air down by some of the friction with the air there. And you're going to produce the most thrust when the blades are pitched at about 45 degrees, with this very simplistic model. In reality, of course, those air molecules are moving around like crazy. This is actually a molecular dynamics simulation of air. So, the blue stuff is nitrogen, and that makes up about 80% of our atmosphere. The red stuff is oxygen, which makes up about 20% of our atmosphere. That's the stuff that you really need to breathe to keep alive. And yeah, it's only 1/5 of our atmosphere. And then there's about 1% of argon. They're the pink balls. And also there's a small amount of water in there from the humidity in the air. But for this example, I'm just going to have the air molecules are sitting there in a static fashion, so it's clearer how these things typically produce thrust. The faster you spin the blades, the more lift you generate, and the lower the air pressure, the less air molecules the blade hits and the less lift it creates. Now, many of you will know that helicopters can't fly very high, but this is a combination of two factors. First of all, the rotors simply can't spin fast enough, and more importantly, there isn't enough air to run the engines. Just like people need that oxygen to burn fuel and create energy, engines need oxygen to burn fuel and create thrust. So as you go up and the atmosphere becomes thinner, the oxygen content of the air becomes less. And eventually it gets so dilute you just can't run an internal combustion engine on it. Thankfully, this isn't a problem with small electric craft. Electric engines don't need that oxygen to burn fuel to create thrust because they've got all the energy they need in the batteries. In principle, the only thing that limits how high an electric helicopter can fly is if it can mechanically spin the blades fast enough in the thinning air. Yes, unless, of course, you actually need the air for cooling. But that's a different story. Now, at this point, you might be saying, hey, if this is all true, why don't we have electric helicopters or electric planes? The simple answer is batteries suck as a way of storing energy, with something like 40 times less energy density than gasoline. You know, and your typical airliner is 30% by mass gasoline. There is simply no way you could pack that much energy into batteries, and even if you could, they would be so insanely dangerous that you would never put them on an aircraft. So let's just say, for an example, that the revolutions per second you need to produce thrust to fly on Earth with this drone is 1 at 1 atmosphere. If you go up to where there's half of the atmosphere, the blades need to spin twice as fast to produce the same lift. And if you go up to where there's 1/100th of the atmosphere, you need to spin the blades about 100 times as fast. Now that's most notably a problem in the forces that it's going to put on the bearings and the blades. So on Mars we're helped out a bit by the fact that there's only 1/3 of the gravity on Mars that there was on Earth, so we only need to maybe spin the blades 30 times faster. And of course you can make the blades much bigger, so you don't have to spin them as fast.
So how fast do the blades have to spin to produce lift?
They have to spin at about 2400 RPM to provide lift.
So how would 2400 RPM, say, compare to a regular RC helicopter with about the same blade length? So the RPM that they're looking at isn't that far off what you can get off a regular remote-controlled helicopter with comparable blade length. So the numbers that they're looking at really aren't that inaccessible here. It looks like what they've mostly done is hugely increase the surface area of the blades such that they don't have to get crazy RPMs out of the rotors. And it's going to be a fascinating craft that probably won't be able to fly on Earth at all, anywhere outside of the vacuum chamber where they test it. Kind of like the lunar lander could only land on the moon. It couldn't actually land on Earth. Now, NASA claims they've had mock-ups of these things flying in a vacuum chamber at about the right pressure, and I can believe that, even if the thing is clearly tethered by a safety wire. Now, NASA's spec of this thing is going to weigh about 1 kilo.
And the mass, the total mass, including everything, the rotors and everything it has to lift, and the camera, everything, is approximately 1 kilogram.
Which is very comparable to a drone that they have on the DJI website. So this commercial drone weighs about 1 kilo. What sort of power does it need to fly? Well, the battery carries some 68 watt-hours of power, which is about 250,000 joules, and will run for about 23 minutes, which is about 1,400 or so seconds, meaning that while this thing is in the air, it's pulling down about 170 watts. And I'm going to say that you need about comparable amounts of power to produce comparable amounts of lift using electric motors, because you just got to put bigger blades on the motor, that sort of thing. Now, NASA reckons that when their drone's in the air, it's going to be running at about 200 watts.
The power that it's going to consume, which, by the way, it has to generate on its own through the solar panels and charge the batteries inside, is 220 watts.
Which seems very generous, especially when you consider you only need about 1/3 of the energy to fly on Mars that you do on Earth.
Right, so the system is designed to fly for 2 to 3 minutes every day. There's a solar panel on the top, and that provides us enough energy for that short flight, as well as to keep us warm through the night.
So let's see if they can actually get that power. They want 220 watts for a 2-minute flight every day. So they need about 26,000 joules from somewhere. The solar panel they have planned, I'm pretty skeptical about that. This is a 40-watt panel. That's when it's pointing straight at the sun and tracking it for the whole day. It generates about a consistent 40 watts. Let's just say that a solar panel that tracks the sun has a 100% efficiency for comparison. Now, if you don't track the sun, you just have a fixed solar panel, then you lose about half of that potential. That is, your solar panel is now operating only at 50% relative efficiency. And if you light flat on the ground, as you would in, say, a road, you're now down to about 30% efficiency. By the simple act of geometrically laying these panels down flat on the ground, you are throwing away about 60%, 2/3 of their potential power generating capability. And what's true for solar roadways here on Earth is also true for solar panels on drones on Mars. So if this solar panel were actually on the drone, it would generate about 1/3 of its maximum power, which averaged over the daylight hours is about 13 watts. However, the sun's only in the sky for half of the day, so averaged over the whole day, it only on average produces about 7 watts. Then, of course, you're on Mars. So Mars only gets about 1/2 the solar flux that you get at Earth, meaning that your solar panels will generate about half of this power. So you're now looking at an average continuous power from a solar panel this size of about 3 watts on a typical Martian day. So given that a Martian day and an Earth day are almost exactly the same length, this means that over a whole day, a panel like this, on average, would produce some 250,000 joules. That's about 10 times what they need for their 2-minute flight. Or alternatively, to get only the right amount for their 2-minute flight, they would need a solar panel about 1/10 of this size, which seems about right for what they have in their designs. That being said, I'm still really skeptical. They're not out of the woods yet. You see, if I was a guessing man, I'd say that when the temperature drops, the batteries or some other critical components freeze. And that's good night, sweet prince, for your helicopter.
So I was doing a nice even flyby or whatever, and it started losing power. When I tried to put power on, nothing happened. At which point you're screwed, because if you try and turn, you lose altitude. And well, anyway, it managed to land out of the sea, but a wave then came in and waxed it. So why did this happen? Well, I think part of the clue comes from the type of sand. So this is what a normal motor should sound like. Yeah? And this is what the motor sounds like on the one that crashed. And if you actually look into the motor, what you actually find is it's coated with black sand, and you can't wash it off to save your life. It's magnetic black sand.
And when they pick up enough of it, the motor fails and your craft crashes. And if you're in a kind of dusty environment, it's maybe something you should think about.